Hey, this is Leach with Simpson Math, and in this video, I'm going to be doing just a kind of a general introduction to probability. Some general terms that we need to know, what even is probability. So let's get started by talking about, well, what is probability? So probability exists on a spectrum between 0% and 100%, or 0 and 1. When I work probability, we often do math at the proportion level, so between 0 and 1, but I often will communicate it as percentage. Of course, report it as your instructor sees fit. So it exists on a spectrum between 0% and 100%, or 0 and 1. 0 or 0% is an impossibility, something that will never, ever happen. And 1 or 100% is a absolute certainty, something that is going to happen, guaranteed to happen. And then the 50% is just that 50% chance. That's that equal chance. Obviously, the closer that we are to 1, the more likely it is to happen. If I have like a 90% chance, you're not guaranteed to happen, but it's a pretty good chance that it could happen. If you have something that's like a 5% chance, then it's not impossible, but pretty low, like a 1 in 20 chance of happening. So just to highlight these points, talking about a coin flip. So if I'm talking about flipping a coin, and I'm talking about the probability of getting a head or getting a tail. So I have a coin on each side. I have either heads or tails on each side. So the probability of getting a head is 50%, or 1/2. Because there's a 1 out of 2 chance, or 50% chance that we do that. And I'll talk about what does it mean, chance, and all that in a minute. Then the probability of getting a head or a tail. That's like a 2 out of 2. It's guaranteed to happen. That's 100%. So if I have a fair coin, not counting about it landing on a side, that's not an option. So it either gets heads or tails. So that is then a 100% chance of happening. The probability of getting, let's say, a dog. My dog's laying over here on the floor. You might hear him click around in a minute. So the probability of getting a dog when you flip a coin, well, that's not going to happen. That's a 0 out of 2, or a 0% chance of happening. So just those 1 out of 2, 2 out of 2, it's basically the proportion, where it's the number of successes on top over the total number of options on bottom. So I had 1 success out of 2 options, 2 successes out of 2 options, 0 successes out of 2 options. So when we're talking about probability, we're thinking about random phenomenon. With random phenomenon, we don't know what's going to happen next. We know what the possible outcomes are, but we do know that in the long run, what it approaches. So that's the main idea of this is, I don't know what's going to happen next. I know in terms of when I'm flipping a coin, I'm either going to get a head or a tail. Don't know which it's going to be, but I do know that in the long run, I have a 50% chance of getting a head or a 50% chance of getting a tail. So yeah, and then for any random phenomenon or trial, it generates an outcome. So here are two kind of vocab terms that we need to know. So a trial is like me flipping a coin or me rolling a dice, some action that is a random phenomenon. Then depending upon what I'm doing, that generates some sort of outcome, some result. If I'm flipping a coin, I'm looking on what's top, heads or tails. If I'm rolling a die, I'm looking at the number. If I'm spinning a spinner, I'm seeing where I've landed. I'm drawing a card, I'm noting what I care about the card. So for example, rolling a fair 6-sided die, that's a D6. I'm going to be doing an abbreviation D6 to represent a 6-sided die, as opposed to like a D20, a 20-sided die, so forth. Each roll is a trial, so every time I roll the die, that's a trial. Then the number rolled on the die, that's that outcome. That's the result that we're measuring. It's highlighted in green because I use that in a second. It's a big deal. Events. So events are specific outcomes. So there's the specific outcomes or combinations of outcomes. This is the input of our probability notation. It can be represented with words, but more formally as a single letter or mathematical statement. So notice I said outcomes or combinations of outcomes. So going back to our example we just had here, if I'm rolling a D6 where each outcome is the number rolled, some possible events could be just me rolling a 5. Notice that is a specific outcome. Or it could be a combination of them. So maybe I'm rolling the number 4 or less. So notice that would be a 1, 2, 3, or 4 I'd be happy with. Maybe it's rolling an even number. There would be a 2, 4, or 6. Maybe it's rolling a prime number. That would be a 2, 3, or 5. 1's not prime. 4 has a factor of 2, and 6 has factors of 2, and 3. So 2, 3, and 5 are the prime numbers between 1, 2, 3, 4, 5, 6. And so that could be a possibility. Notice these are outcomes where technically I would say each outcome is the number on the die roll. And then here, these are the combinations of said outcomes. This event is the input in our probability notation. So let's talk about that probability notation. So the probability notation that we're using throughout this course, and whoa, that green is blinding. It's the probability of, so this knows that probability of, see how I read this, probability of, oops, I'm missing my end quotes here. Boop, boop, there we go. This behaves just like our function notation, so like f of x, but instead of like a lowercase f or whatever we're using to name the function, we're using a capital P to represent that probability of. So probability of my event equals the probability. Sometimes students get a little confused and they'll stick the probability inside there, and that's backwards. We're going to put our event in here, and then whatever the probability of that event is will produce some output, and that output is my probability. So just for example, here are 3 kind of examples. And I think I said up here that events can be represented with words, or but more formally as a single letter or a mathematical statement. So let's look at all 3 of those cases. So I could say, well, my event is me rolling a 5 on a 6-sided die, on a d6. So that's using words. So I would read this as the probability of rolling a 5 on a d6 is 1/6. We can also formally define the events with a capital letter, and when we do probability notations, it's typically with a capital letter. So I can let capital A represent rolling a 5 on a d6, so that very specific event. And then I can, instead of having to write all those words, I could just write P of A. Why might that be helpful? Because maybe I'm going to be doing some problems where event A is rolling a 5 on a d6, and maybe event B is spinning red on some sort of spinner or something. And I want to find the probability that I get this, or this, or this, and this happens, or different things. And instead of writing all these words every time, we can just kind of shorthand with A. There's no special letter. I might do maybe F for 5, or R for roll, or D for dice, if I'm kind of getting to pick things myself. But, so the idea is you can just name it and then use it. We also could define the event as kind of more of a mathematical statement. So here I'm saying let D, and I picked D for dice, just be the result of rolling a d6. So I'm not saying what is the specific outcome. That's just kind of the trial that's happening. That's what we're doing. We're rolling a d6, rolling a 6-sided die. But here I could have the event is where D is 5. So my results of rolling a d6, and say D is 5. Or D is less than or equal to 4. So the likelihood that I get a 5 out of a 6-sided die, they're all equally likely, so I have a 1/6 chance of that happening. Or less than or equal to 4, so that'd be a 1, 2, 3, 4, just like what I described up here. And that is a 4/6 or 2/3 or 0.6 repeating. So notice how there are different ways we could do this. For my classes, I tend to kind of just do whatever kind of makes sense in the situation. If it's too hard to explain in symbols, just write in words. Especially if you're going to be doing something multiple times, you might want to give it a label. And especially later, when we start using random variables, this will be a big help. We'll definitely be doing that a lot. So the sample space, which we often just shorthand as a capital S, is a collection of all possible outcomes. So you know how I said you can pick your letters. Maybe don't pick capital S because we do kind of reserve it for sample space, but as long as you define it, then it should be fine. So the probability of getting results from your sample space is 1. So our sample space in rolling a 6-sided die is 1, 2, 3, 4, 5, 6. So those are my 6 possible outcomes. So the probability that I get a 1, 2, 3, 4, 5, or 6 is 6 out of 6 or 1. So the probability that I get anything out of my sample space is 1. The probability I get anything outside of my sample space is 0. So earlier at the beginning of the video when I said the probability that I get a head or a tail, that's me getting something out of my sample space. My options are heads or tails, so as long as I get a head or a tail, I'm happy. I'll talk more about this in a later video, but or is as long as you have a success, it's all good. You don't have to have, you can have one or the other or both. It doesn't really matter here because you can't get both. So that's that situation. So then Notice if you try to get a value outside of your sample space, that's impossible. So if I'm rolling a 6-sided die, I could not get a 7. That's not a possibility. All right, let's talk about some probability models or probability distributions, depending upon kind of what they're basically the same thing, depending on who might define it. So we've already talked about these two facts. Let's just document them, that both of these things need to be true for a valid probability model. So all probabilities in your model must be valid, meaning they must be between 0 and 1 inclusively. If it's 0, it's kind of silly to maybe include it, but maybe, maybe I crafted a die and I stuck a number on it somewhere and it can never ever land on that as a bit of a joke. So maybe that would be 0, a 0% probability. If it's a 100% probability of something happening, then it's a pretty boring probability model because it's something that will always happen. I saw a video the other day of someone who had a D1, a die that will always land on, that top is kind of warped and weird. So it would be a pretty boring probability model, but that would be fine. So the sum of all, and I do include here non-overlapping probabilities, is 1. I'll talk more about that in one sec. So then basically that means our sample space, of course, has to add to 1. So both of these would be valid probability models when rolling a d6. So looking at this first one, it could be, this is just me, my x, the x value here is just the outcome on the die. It could get a 1, a 2, a 3, a 4, a 5, or 6. And there's a 1/6 chance that each of those things happen. Cool. I could maybe craft it to be a little bit different. Maybe I want to find that, maybe for some reason I group together getting a 1, 2, or 3. And then I group together a 4 or a 5, and then I group together a 6. So notice there's a 3/6 chance of getting a 1, 2, or 3, a 2/6 chance of getting a 4 or 5, and a 1/6 for getting the 6th. Personally, when I'm working with probability models, especially in later topics, I usually won't reduce unless I have to, unless I'm told to, but I don't like reducing things because it just makes the math be a little bit messier, and it's nice to see that I can clearly add that up and get 6/6. But of course, 3/6 is 1/2 and 2/6 is 1/3. So let's talk about some invalid probability models. I don't want to write any examples of them, but just things to look out for. I'm just getting rid of that spell check. That's not necessary. So invalid probabilities such as negative numbers or numbers larger than 1. So 1 or 100%. You got to make sure watch out for that because this condition needs to be satisfied. Probability models not adding to 1 or 100%. That would be violating this one here. That's likely due to maybe forgetting about some possible outcomes. And maybe if you're doing it yourself, common error is maybe you're running a store and you're wanting to keep track of the number of books purchased per checkout. So maybe they didn't purchase any books, but they bought like a bookmark, or they bought maybe just a muffin from your cafe or something. So 0 books purchased, or 1 book or 2 book or 3 books. You don't want to just stop at 0, 1, 2, and 3, because obviously there could be more things. Someone could have bought a stack of books. And maybe it gets a little, trivial and tedious trying to count up or imagine the most that someone would buy. So you would want to say something like 4 or more. Once you hit your that's far enough, I want to then look at the rest of that. Sometimes you may want to include or more. I did not need to do an or more in a die rolling because my options are 1, 2, 3, 4, 5, 6, period. But in terms of this kind of more real life data, you could get 4 or more. You can get more than 4 die rolls, so you would want to make sure that you include that. In this particular case, if you do this 0, 1, 2, 3, 4 or more, then that would be valid for at least that structure. And of course, all those probabilities each would need to all be valid and add to 1. And then lastly, just talking about overlapping outcomes. So for some reason, I wanted to make a table like I had above, and I had one of these was even, one was odd, one was prime, one was just the number 6. That would not be a valid probability model because while even and odd are distinct, separate groupings, prime has both even and odd numbers. 6 is in the even group. So we can't do that because it's overlapping. If I add up those probabilities, my probabilities would be more than 1. So we want to make sure that that's why I have this non-overlapping. We're kind of define a non-overlapping term, that term in a later video. All right, so take a look at this quick example here. So we have, this says many stores run secret sales. Shoppers receive cards that determine how large a discount they get, but the percentage is revealed only after the purchase has been totaled at the cash register. The store is required to reveal in the fine print the distribution of discounts available. Are each of these probability assignments plausible? Why or why not? So I do have the answers already revealed here, but let's talk about them. So on here, if I look at this, I'm peeking at my probabilities. I see that all of them are valid probabilities, but if I add these up, if I add up row A's probabilities together, notice we get way bigger than 1. So this is not a valid probability model. If they try to report this, someone would get upset because that looks like 160 total percent. That's a problem. Someone would get upset. Some regulating agency would be like, hey, you're running a promotion, but it's a bit of a scam. So it's not a proportional thing because this needs to be out of a total percent. So that's why it's more than 1, so it's not plausible. All right, take a look at this next one. That one's cool, that one's cool. Oop, it already feels bigger than 1. Oh, and also we have negative numbers. So I cannot have any probabilities that are negative or bigger than 1. And then, of course, it needs to add to 1. So here this says at least one probability is not between 0 and 1. And I think also in this case, if I do add them up, notice those cancel out and it does add to 1. So it's not a both situation here because if I did add them, I would get 0. I would get 1. So that's a little bit of that just pickiness. But again, it's not possible because we have a non-valid probability here. C, this one's pretty good. It's maybe not a very exciting one. If you read the fine print, it'd be like, you could get up to 50% off. But it's kind of impossible to get 50% off. Then that would be kind of a potential problem. 1 sec. Hey, Johnny, can you call Marty? You might have seen my dog, Marty, needed he was circling me. Okay. So this is a valid probability here. Valid probability model. Boring, though, because they do all add to 1, and they're all are between 0 and 1, but it's not a very exciting one. This one, as you can see, they are all valid, but they add up to be 0.8, so that is not a valid probability model. And then lastly, this one would work, and this one would kind of make sense as to how you might run it in the store. 80% of them are 10% off. You have a 10% chance for 20% off, and then 1 out of 20 of them each is 30 and 50%. That kind of makes sense. You have a chance to get there, but most people would just get 10% off. Here in Texas, it's basically just a little bit more than the tax off. All right, so let's talk about what in the world is this probability thing I keep talking about. So I like to think of it as the long run percentage. This is the long run percentage of results that satisfy our outcome. So I'm actually just going to switch my screen. To here. All right, so this is a website. It's at this website that's on the screen, just to kind of cite them. So what I have programmed in here is I've set the probability of success here, the probability you'll see it'll talk about coin flips in a sec. So it's like, imagine I've taken my coin, a 50-50 coin, warped it, weighted it weird, so that way I get a head 17% of the time. What I'm really modeling is trying to roll a 5 on a coin, on a 6-sided die. So rolling a specific outcome on a 6-sided die, that's 1 out of 6 or 0.1666 repeating, so it rounds to 0.17. So suppose that's the case here. I have this 0.17, so let's call this 1/6. And these are the results of the first 10 die rolls. Sorry, coin flips. I meant to say die rolls. It does say a head in the first flip because it's talking about coins. I'm talking about a die roll. Sorry to be confusing. So in this first case, it might be hard to see, but there's a 1 right here. So in my first die roll, I got a head. So I have 1 out of 1 head. Or sorry, 1 out of 1 5. All right, then on my second die roll, I did not get a 5. So now I'm at 1 out of 2. My third one did not get a 5. Fourth one did not get a 5. Fifth one did not get a 5. Sixth one did not get a 5. And notice it's kind of what we expect, that 1 out of the first 6, within 1 of the first 6, I get a 5. That kind of makes sense here. Notice it started high and then kind of dipped down low pretty quickly. Open on the 7th one, I did get a 5 and it went up. Notice how it went up, and now we're at about like a 30, about 30% of the time we've gotten a 5. Oh, the 8th time we didn't, it went down. Oh, lucky me, the 9th time it went back up. And so now we're maybe about 35-ish or so percent of the time we get ahead. Oh, actually, I can do that math. 33. That'd be 3 out of 9, or 1/3. And then a 10th, we didn't. I can do this more and more and more. So I'm going to make this happen more. Here's about the first 40. So notice we did make it up to about that 33%. And then we had a string of nopes. It even dipped down less than my 1/6. Then my 20th one went back up and then went way down under and then kind of working its way back up. Let's look at more. Eventually those dots will go away like that. And you'll see that as I do more and more and more coin flips, it's fluctuating. It's getting maybe in theory closer to that line. As I do more and more, you see, yep, it's approaching and getting closer. It can get close and then kind of still wiggle off. And then I can get all the way up to 1,000. So I had no guarantee. Actually, a second ago when I was this far away, when I was like, oh dear, when I get to the end, am I even going to be close to 1,000? I mean, be close to 1/7, 1/6 rather. And yeah, we were. We're actually a little bit over. We're at about 18%. We should be at 17. But it's going to wiggle and fluctuate. It's going to be harder for it to wiggle off. But I know that in the long run, we're going to be getting closer and closer and closer to that value. That value being our actual probability here, labeled lowercase p. All right, so I have this kind of summarized here. And the idea is that this is the mindset of our probability. It's the long run percentage of results that satisfy our outcome. In the long run, we expect about 1/6, about 16.6% of the time that we would be getting a 5. But we're no guarantee that we're wanting to get that. It should be getting closer and closer. If you notice that the two images I have on the screen are a little bit different, I did try to find one that started out. I could like re-randomize it. I did seek one out that started at 1, so we saw more noticeable change. But after that, everything was random. You see that's a little bit different than what we saw a second ago. So that's what I mean by long run. We'll see. We have a rule for this in a second. We'll come back to this. But I need to first talk about the term independence. So things are independent from one trial to the next. So things are independent when it says the outcome of one trial does not influence or change the outcome of another. So things like coin flips, die rolls, spins of a spinner, they're inherently independent. If I flip a coin 10 times and never get a 5, there's no memory in that coin. That coin doesn't go, ooh, I'm due a 5. If I flip this coin 100 times and never get a 5, this coin doesn't even further. It's like, I need a 5. And then suppose I hand it off to my husband and say, hey, flip a coin. He's not any more or less likely to get a 5, assuming it's or not flip a coin. I'm mixing metaphors. Just rolling a die or flipping a coin. Any of those things, they don't have memory. So similar things with like spinners. So they're inherently independent. But suppose I'm selecting items from a collection of objects. So I have a deck of cards, I'm going to select a card out of it. Or I have marbles in a bag, and I'm going to reach in the bag and pull out a marble and note its color or something. Or things like the lottery system, the ping pong balls that you read that the machine pops out one of the random balls. So if I'm selecting objects from a collection of objects, that drawn objects should be replaced in order for it to maintain independence. Think about in the lotto system, when one of the ping pong balls with the number pops out, it pops out and it goes down to this little separate little platform, this little tube that the camera is looking at. That ball does not go back in. Lotto numbers are not independent from each other. So that one number's gone out and I can't get that one number again. So that is not independent. So independence should be maintained if a single object was drawn from multiple collections. If we're dealing with if we're wanting that independence. No, not would. I said should. I meant to say would. Independence would be maintained if a single object was drawn from multiple collections. So let's say I have 5 different decks of cards. I'm going to deal one card from each deck. each of those card draws would be independent, because I could get an ace of spades, and then from the next deck I could get another ace of spades, or if I have cards and then marbles. So that's all good. So you'll see it often with probability things, sometimes with replacement or without replacement, whether you're putting the thing back in or not, if you're drawing things from a collection. All right, I needed to define that independence because of this line. If trials are independent, then as the number of trials increase, the long run relative frequency of any outcome gets closer and closer to a single value. That single value is what we're calling this probability. So that's what's happening here. This proportion here, so after six die rolls, I had 1 out of 6 fives, and so that was that relative proportion. But then here it was 2 out of 7, so I had it updated, and then over time we notice that it's getting closer and closer to that 1/7, and all of these numbers that we're calculating is that relative proportion, or that relative frequency. So law of large numbers goes to, like, I know we stopped at 1,000 here, but really we're talking about as this goes to infinity, that we know that this will approach that, or this will approach that value. Let me go back to the very first thing we talked about. Oh, not very, almost the very first thing, random phenomena. We know the possible outcomes, heads, tails, 1, 2, 3, 4, 5, 6, whatever it is. We don't know what's going to happen next. I have no idea what's going to happen next when I roll a die or flip a coin, but I do know their long run behavior. I know that in the long run, when I roll a fair die, I get a 5 1/6 of the time. When I flip a coin, I get a head one half of the time, 50% of the time. I'm going to, where am I? Here we are. So in the long run, that's what we're expecting to get. There's some people who get a little bit confused by the law of large numbers. They might have learned it as something called the law of averages, and this is an incorrect idea. So a lot of times people are wanting things to balance out in the short term. They're thinking that probability events have some sort of memories. They don't. In the long run, we expect them to balance out, but I'm talking about approaching infinity with the law of large numbers. An evening spent playing in a casino does not even come close to infinity. You're not like, oh, I've been losing all night. I'm due for a win any minute now. That's not how that works. If you were to play for infinity, if you're caught in that casino in Percy Jackson, then you might have a chance of actually getting there. But again, the house is rigged, so you're going to be losing on average. We're not due any certain outcome. And then randomness can produce streaks longer than expected is kind of the last thing I want to point out, that we saw up here how kind of streaky some of these were when I zoomed in. Like you saw like runs of losses, or even like runs of kind of unsurprising wins. Randomness is a whole lot streaky than we as humans expect it to be. So we often will go in long streaks of losses or wins. And that's perfectly fine, because we don't have to balance it out in any certain time frame with our sense. Law of large numbers again goes to infinity. All right. So last thing we're going to talk about are just different types of probability. There are 3 types of probability. There's the empirical probability. I don't really like that word. Empirical gets used a lot in math. It's just, empirical is a sciencey word for just observed, but it gets used a lot in weird senses, like it's like some special vocabulary term, but it just means observed. So I just think this day and age is just a weird word. So I like to think of it as just our observed probability. So it's a relative frequency, or which we often communicate it as a proportion or percent, the fixed number of repeated trials. So it's just a basic proportion. So notice on my numerator, this is what we've been doing all day. It's the number of outcomes satisfying A divided by my total number of outcomes. So I have a lot of dice over here. Let me pull up one of them. So I have a whoops. So these are regular 6-sided dice, that you're used to seeing in like playing Monopoly or something. Let me take it out of the bag, and so it's not just liquidy plastic. So here's just a regular 6-sided die that you're used to seeing. I'm a nerd. I like to have weird dice. So this is another 6-sided die, but it looks like a fireball. It's a D6 fireball, because when you play tabletop games like Dungeons & Dragons, often when you cast a fireball spell, it can do up to 6 points of damage, or that's the modifier at least. So this is a cool little fireball. I have a nephew who took this took that and molded it and made a mold of that, and then cast a custom die then from that. So I have this die. One, I don't know if this die is fair. It should be. But what about his handmade die that he did? So I'm curious about this die. So my example says, my nephew made a custom D6. Is it fair? So suppose that I rolled this D6 60 times and I get 13 fives. Later in the course, we're going to talk about that is it fair question. But let's just talk about the probability behind that. The empirical or the observed probability from that would be the probability of getting a 5 from my nephew's die. I observed 13 successes, so this is numerator, out of 60 total attempts, or about a little bit more than 21%. So it should be, about 16 repeating. It's a little bit high. Is that too high to be concerned? That's a topic later in the course. But so that's my observed probability. I don't know it in theory. I can't, I haven't rolled this die 1,000 times, or sorry, in an infinite number of times, but I have done it 60, and I got this. So that's my observed probability. The theoretical probability, or often just when we refer to just probability, we're talking about the probability in theory. This is the probability based on the law of large numbers. It's the long run average. Most of the rest of the course, pretty much, I think in every chapter, we're going to touch on some version of probability. Even the rest of this, so this finding the probability will be a thing that we're going to be doing throughout the course for a lot of different purposes. So in theory, just simple ones again, talking about dice. A fair D6 gives me a 5 one time out of 6 rolls. So by the law of large numbers, that is a 1/6 chance of getting or 1/6 probability of getting a 5 out of a D6. Then, and just to backtrack, just to see this in words, when you have equally likely outcomes, you can just treat it as that proportion. So I have one thing that will give me a success out of 6 total things. When they're equally likely, we just do it as a proportion like that. But that should be something you covered in literally middle school. Lastly, personal or anecdotal probability. This is subjective and based on personal experience. So let's say that you have a doctor is estimating the amount of time that a terminal patient has left to live. They say with maybe 80% chance that they might live six more months. And a little bit more, but that's kind of that idea that we kind of will hear the most often. Someone giving that just kind of a probability based on their experience, their life, their lived experiences, just kind of that probability. Like, a farmer being like, look at those clouds. When I see clouds like that, 90% of the time rain's about to be coming this way. Sometimes it doesn't, or whatever it is. All right, I think, that's all. I hope this introduction helps. If you're watching my videos on a playlist, it should be the next one to load up, or go ahead and check out my next video when we're going to be talking about the probability rules, so basic probability, and start doing a little bit more calculations. So I hope this helps. And I'll see y'all in the next one. Bye.